Okay, good evening. So let's start.
Yes, sir.
Okay, so let us move to the first question of today. So this is the question number 51 of GATE 2016 Metallurgical Engineering. So for a polymer reinforced with 40 volume percent glass fiber, the elastic modulus in gigapascal along the transverse direction is 5. Option A 5.6, option B 8.1, option C 30.1, and option D 43.4. So now the elastic modulus of the glass fiber and the polymer is given. So we have to calculate the elastic modulus of this composite in the transverse direction. So that means, let's say this is the ceramic, this is the composite. Sorry, this is the composite, and these are the glass fiber. Let's say. So we have to calculate the modulus in the transverse direction. That means we have to apply load perpendicular to this direction of the glass fiber, orientation of this glass fiber. So let's say we are loading it in this in the transverse direction, and applied load is F. And let's say the area, this area of this surface is A. Okay. So uh, okay, first you tell me what is the elastic modulus. Do you know what is elastic modulus?
Force upon area.
No, elastic modulus is when you are loading a sample elastically, then that ratio of the stress versus strain is elastic modulus. That is sigma by epsilon is elastic modulus. So sigma by epsilon is elastic modulus. So you can write that stress is equal to elastic modulus into epsilon. So this is the relationship between the stress and strain with the elastic modulus. Like, let's say if this is a stress strain curve, so first it deforms elastically, right? Then it goes to the plastic region. So up to this elastic region, so the ratio between the stress and stress is basically elastic modulus. So now, so we have to calculate the elastic modulus in the transverse direction. So now, if we apply load in this transverse direction F, and these are the glass fiber, and this other part as the matrix, right? So the force on the matrix, that's is Fm, and force in the fiber is F of small f, should be equal to the force on the composite. Otherwise, what will happen if the forces are not equal? Then what will happen there? This in this area, this will break. So there should be a force equilibrium between this matrix and the fiber, right? So from the force equilibrium, we get that force on the matrix is equal to the force on the fiber, and force on the is equal to the force on the composite. Now also we can see, if we are loading in the transverse direction, this area A is also same for the matrix part and for the glass fiber part. So that means if A is same, then what will be the sigma? Sigma m will be Fm by Am. Okay. Now this force is also same and A is also same. That means Fm by A. Similarly for fiber, it will be F of fiber divided by A of fiber. So it is also, let's say this is equal to F. So this will be also F by A. Sorry. So this will be also F by A. And similarly sigma C, that means stress on the ceramic will also be equal to the force on the ceramic divided by area of the sorry, not ceramic, it is composite. So on the composite, so it will be also F by A. So that means what we got, sigma M is equal to sigma F is equal to sigma C. That means for stress on the matrix is equal to the stress on the fiber is equal to the stress on the composite. Now, from the geometry of the deformation, if we like extend this polymer in the transverse direction, what will be the total strain? Total strain can be written as total strain, let's say strain in the composite, it will be equal to the volume fraction of the fiber into strain in the fiber plus volume fraction of the volume fraction of the matrix into strain of the matrix. So this will be the total strain, right? So you got it up to this point. If you have any doubt, just let me know, then we will move further. You know what is composite, right? Composite means, let's say there is a polymer and you have put glass fiber inside. Or you can also take a simple example like that wall of inside of a home in the village area, we see like that they use bamboo and that mud to prepare the wall. So that also you can like it is same kind of structure like a composite. So there one is a matrix phase which is a relatively soft, and another one is the glass fiber or fiber phase, which is relatively hard. So you can see that elastic modulus of the fiber is more as compared to the matrix. So now you can load this composite structure in two direction, either in the transverse direction or in the longitudinal direction. So here in this question they ask in the transverse direction. So when you are loading the composite in the transverse direction, so let's say this like here these are the glass fiber. So that force in on the matrix should be equal to the force on the matrix should be equal to the force on the fiber. Otherwise what will happen, so this will get separated, that means that failures occurs, right? So in order to so that's why you all have to have that force equilibrium at the junction of this fiber and at the matrix. So that is why the force on the matrix is equal to the force on the fiber is equal to the force on the composite. So let's say we write it as F. Now similarly the area is also same for both the matrix area and the uh, fiber area, means glass fiber. So that is why that sigma, that is sigma means force by area, this is also same for fiber, matrix and the composite. So now when you are deforming like this, so at the same time matrix will also get deformed, and at the same time that fiber will also deform, right? So strain you can write as volume fraction of total strain you can write as volume fraction of that fiber and the volume fraction into the strain in the fiber plus volume fraction of the matrix into strain in the matrix. So now if we apply this stress and strain relationship, so that means what will be the epsilon? Epsilon will be sigma by E, right? Elastic modulus. So in this case, so it will be sigma C divided by E C is equal to volume fraction of fiber into sigma in fiber divided by elastic modulus of fiber plus volume fraction of matrix into sigma of matrix divided by elastic modulus of the matrix. Now you can see this sigma m, sigma f and sigma c all are equal. So simply this will be cancelled out because these are equal to the same stress. So, so this will cancel out. So what will be the relation then? 1 by elastic modulus of the composite in the transverse direction. Let's say T is for transverse direction as we are loading in the transverse direction. So one elastic modulus, 1 by elastic modulus of the composite in the transverse direction is equal to volume fraction of the fiber divided by the elastic modulus of the fiber plus volume fraction of the matrix divided by the elastic modulus of the matrix. So this is the relation between the elastic modulus of the composite with the elastic modulus of the fiber and the matrix. Now what are the values are given to us? Volume fraction of the fiber is given. So V of F is given. This is 40%. That means fraction is 0.4, right? So then what will be the volume fraction of the matrix then? Anyone?
0.6.
Yes. So 1 minus 0.4, that means 0.6. Now also the E of fiber is given to us, that is 70 gigapascal, and also E of polymer or matrix. Here matrix is the polymer, so that's why E of M is 3.5. It is also given to us. So this is known, this is also known, this is known, this is known. So we need to calculate this one, right? So now let us put this values to this equation. So what will be the value of EC then? Okay, sorry. So 1 by E C in the transverse direction is equal to volume fraction of the fiber, that means 0.4 divided by the 70 gigapascal plus 0.6 divided by the 3.5 gigapascal, right? So then what will be the elastic modulus? It will be 70 into 3.5 divided by 0.4 into 3.5 plus 0.6 into 70. So now if you calculate this one, you will get the elastic modulus in the transverse direction. So can anyone calculate and let me know the answer? Anyone calculated? What answer you are getting?
0.171.
0.171. Have you calculated it properly? It is 70 into 3.5 divided by 0.4 into 3.5 plus 0.6 into 70. This is plus. It will come 5.64. Check it once again. Are you getting the same or not? Others are getting this value. Devendra, Manas, have you calculated?
Yes, sir. Calculate, sir.
5.64.
Yes, it is 5.64. Because you got it?
Yes, sir. I have just calculated the value of addition. After that, we have to transpose. So I have not transposed. Or I just calculated the value of 1 by E 3 by transpose.
Okay,
Then
okay.
it's come to around 30.
Mm-hmm. So now we got it direct. So the you can see this answer is then this one, option A, 5.6. Okay. So now this was the one case where the polymer is this composite is loaded in the transverse direction. Now if I ask you that what will be the elastic modulus if I load this polymer in the uh, let's say longitudinal direction, that means like this. Can you solve this one then? I'm just modifying this question a little bit. So let's say your composite is like this. So now you are loading in the longitudinal direction. Earlier we were loaded in this direction, right? Now we are loading in the longitudinal direction. So in that case, what will be the sorry? In that case, what will be the elastic modulus? Do you know how to approach it? Anyone? If you have anything in your mind, then you can share. So I want to see that are you going to the same direction or not? Before that, have you understood this part up to this part, right? In the transverse direction, how I have calculated. So this is a basically important formula for the transverse direction. You can note down this formula. So if you know this formula directly, you can calculate. that elastic modulus in the transverse direction. So here I am just derived this formula. How to derive it? I have explained all the steps. So this is the formula for the transverse direction. So similarly, in case of longitudinal direction, the formula is elastic modulus of the composite in the longitudinal direction is equal to the volume fraction of the fiber into elastic modulus of the fiber plus volume fraction of the matrix into elastic modulus of the matrix. So this will follow like simply the mixture kind of rule. So in so this is the formula for the if you load in the longitudinal direction. And this is for longitudinal direction, and the previous one is for the uh, transverse direction. So any type of the question may come in the gate. So in 2016 this question comes in that you have to calculate in the transverse direction. I think there is also similar question in 2014 also. There they have asked how to what will be the elastic modulus in the longitudinal direction. So for this then you have to use this formula. So you just can note down this formula. So do you know how this formula is coming? How can we derive this one? Anyone? Okay, first calculate the elastic modulus in the longitudinal direction using this formula. Then let me know the answer. All the value are given, right? VF you know, EF also you know, VM is also know, you know, and EM also you know, right? I'm writing this thing again once again here. So VF means volume fraction of the fiber, that is 0.4. VM is also given, that is 0.6, that will be 1 minus 0.4. EF is also given 70 gigapascal, and EM is also given 3.5 gigapascal. So now you can calculate like what will be the elastic modulus in the longitudinal direction. Just let me know the answer after calculating. Are you guys are calculating? Hello?
30.1.
30.1. Others are also getting the same answer. Devendra and Manas, you are also getting the same answer or not? 72.5. Is it? Devendra, you check once again your calculation. It should come 30.1. VF is 0.4, EF is 70, and VM is 0.6, and EM is 3.5. So it will come 30.1 gigapascal. So if you load along the longitudinal direction, that means if you load like this, then your elastic modulus is 30.1 gigapascal. And but if you load in the transverse direction, that is like this one, then your elastic modulus in the transverse direction is how much you got? 5.6, right? Earlier answer, huh? So you can see that same composite you have, but if you are loading in other direction, then your elastic modulus is different, right? That means this composite is not isotropic in all the direction. If you are loading in the longitudinal direction, you will get higher elastic modulus. If you load in along the transverse direction, then you will get lower elastic modulus. right? So everyone understood up to this part?
Yes,
Yes,
sir.
30.1. Okay, so do you people want me to derive this formula also, how we are getting this thing, or you people can derive by your own? Anyone? So what?
Derivation कर दीजिए.
So should I derive this one also?
Yes, sir.
Okay. So now let's say this is the composite and fiber is oriented in this direction. So longitudinal direction means we are loading along this direction, right? If so after sometimes let's say means after deformation, that is after elastic deformation, this length will increase a bit because of the elastic deformation, right? But you have to keep the loading. Otherwise, if you release this load, it will again go back to its previous shape, means previous shape, because it is under elastic loading. Elastic deformation only happens, not plastic deformation, right? So you can see that when that length is getting changed, both the matrix and fiber is that deformation is same. That length change is same for both. Let's say, sorry, because as for the reference, I am drawing it in the same level. Then it will be better. Hmm. Let's say this length change, that is delta L, is same for the matrix and as well as same for the fiber, right? So what it means, epsilon is, what is epsilon? Delta L by L, L naught, right? So epsilon will be same for the matrix and the fiber, right? So epsilon will be same for the fiber and the matrix, and also will be same for the composite, because that length change will be similar if you load along the longitudinal direction. So in earlier case that force was same. In this case, what is same? Epsilon, that is strain, is same. Now force is F on the composite. We are applying F force. So now let's say the area of the matrix is AM and area of the fiber is AF. Okay. So that means area of this all the fiber together. So like this area, this area. If you accumulate this total area of the fiber is AF, and if you accumulate this matrix part, that means this area plus this area plus this area plus this one. So this area, let's say, is AM. Okay. So now you know what is the relationship between the uh, force and the stress, right? What is stress? Sigma F. Then what will be sigma F? Sigma F will be force on the fiber divided by the area of the fiber. Similarly, sigma M, what it will be? Sigma M will be force on the matrix divided by the area of the matrix. So now, if you write in terms of F in terms of sigma and area, so force on the fiber is equal to sigma of F into area of F. So this is one relation for the fiber, and similarly for the matrix you will get F of M is equal to sigma M area M, right? So now your force has to be balanced, right? So the total force should be, force on the composite should be force on the matrix plus force on the fiber, because you are applying the force over, means force here along this composite, right? So now this force will be divided into a matrix part and into the, and for the fiber part also. So but total force has to be balanced. So now if we put this here, if, so similarly FC will also be, you can write, so like this also you can write F of C is sigma c and A of c, right? So now if we write this force in terms of sigma and area, so it will be sigma c A of c is equal to sigma m am plus sigma f a f. Now let us just take AC in that side, so it will be AM divided by AC plus sigma F into AF divided by the AC. Now if the thickness is, let's say, X or something, so thickness will be same for this matrix also and this uh, poly, fiber also, right? So if the thickness is same, then what will be the AM by AC into X by X, that means VF by V, total volume, right? Volume of the composite means total volume. So that means simply volume of the fiber, this is capital V. So volume of the fiber divided by the total volume means volume fraction of the fiber. Similarly, sorry, this is I'm writing in terms of matrix, right? So this is matrix. So similarly for fiber also you can write area of fiber into thickness is X into AC into X. So this will be volume of the fiber divided by the total volume. So this is volume fraction of the fiber. So it will be sigma m into Vm plus sigma f Vf. Sigma c is this one, right? So now this is stress. This is not elastic modulus. So now what is the relationship between stress and elastic modulus? Sigma is E into epsilon, right? So here epsilon is same for uh, fiber, for the matrix and for the composite. So now you can write it as, so sigma c means then sigma c is E c into epsilon is equal to E of m Vm into epsilon plus E of f epsilon into V of f. So now this epsilon will cancel out because epsilon is same for all the phases. That means polymer and the glass fiber also. So in this case, this equation will be EC. That means elastic modulus of the composite in the longitudinal direction. So here it will be L for longitudinal direction. So it will be equal to the elastic modulus of the matrix into volume fraction of the matrix plus elastic modulus of the fiber into volume fraction of the fiber. So you got this one? How we are getting this formula? By the way, this writing is feasible here, or are you guys having any problem? Because
Yes,
I
yes, sir, visible.
okay. So you people got it right. Means in this case, epsilon is same for the matrix, for the fiber, and for the composite. And the earlier case, what was there? Earlier case, your sigma was same. Stress on the matrix and this sigma was same, right? So this is the difference. That is why you are getting two different kind of relationship. So just note down this formula and that formula. So these two formula is very important. This one and this one. These two formula you just note down. So if you know these two formula, you just can easily calculate what is the elastic modulus in the transverse direction and in the longitudinal direction.
Sir,
Yes.
please explain from that part of AM into X by EC by X, how calculated by you.
Uh, can you repeat your
Start,
question?
sir, I want to just explain the part when you are explaining the you're calculating the value of VM, that is it is in
Okay, okay, this
right
one,
side.
right?
Yes, sir.
Okay, okay, just then just go into a new page. Oh, sorry, these are not getting okay. So I'm doing it in the last page one. So let's say this is your now initially I drawn this composite like 2 dimension, right? So basically it is a 3 dimension body. So this area we have taken. So we are loading in this direction, right? So this area we have we tell that this area is A, and now uh, but there is A means total area of A, that is AC. Now we have composite here. If you see this cross section, you have this fiber will be like this, oriented like this. So these are the fibers. Like if you visualize in this thing in three-dimensional, so this will be the fiber. So the fiber will also have some area. So the total area of the fiber is AF, and the area of the matrix is AM. So that means basically you can write that total area is equal to AF plus AM, right? Now what I told that time, that how we are getting, what will the volume of this total thing? Volume of the total thing will be area AC into total height. So you can write it as X also, or you can write it as H also. So there I have write it as X. So let's say the height is X. So AC into X will be your volume, total volume, right? Now what will be the volume fraction of the fiber? Volume fraction of fiber means volume of the fiber divided by the total volume, right? So now what will be the volume of the fiber? Volume of the fiber will be area of the fiber, that is AF into this height, because fiber is also having the same length as of the composite, right? So this height will be same both for the fiber and both means for the fiber, for the composite, and for the matrix. So this height of the fiber is also X. So that means X. This is the volume of the fiber, right? Divided by the V. V means what? AC into X. So that means what you are getting, AF by AC is basically volume fraction of the fiber. Similarly, for the matrix also you will get volume fraction of the matrix is what? Volume of the matrix divided by the total volume of the composite, right? So here also, what is the volume of the matrix? Area of the matrix into this height. Height is also same because it is the same body, right? That total height is same for everything. That matrix, that fiber, and also that composite. So height is same. Can you visualize this one? Why height is same, right? Or how I am getting this one? Now you understood, or because
Yes, understood, sir.
yes. So then what I am doing, this AF by AC and AM by AC. I am just replacing this in terms of VF by V and VM. So as you can see there, okay, this here just I have replaced this thing, this ratio. This ratio I have replaced in terms of VM, and this one in terms of VF. That is how we are getting this thing. So is it okay?
Yes,
So
sir.
should I move to the next question then? Okay, so now let's move to the next question. So this is the question number 25 of GATE 2014, metallurgical engineering. So the question states that which one of the following signals from the specimen is used in a scanning electron microscope to get quantitative elemental analysis? So quantitative elemental analysis. So option A is secondary electron, option B is backscatter, option C is X-ray, and option D is transmitted electrons. Okay. So what is quantitative elemental analysis? Means how much quantity of that element is present, right? So in scanning electron microscope, okay, which signal? Anyone know the answer? Anyone? Before I proceed, anyone want to answer? What will be the answer?
Can I guess, sir?
Mm-hmm.
X-ray.
Uh, because you are saying X-ray, and Devendra,
Okay.
you are saying option A, secondary electron. Manas, you also try to answer. Okay. Uh, you are saying option B. Okay. So basically, first let us understand this question first. So there is different type of signal generates when that electron interacts with the specimen, right? In a scanning electron microscope. So so one type of signal is secondary, another is backscatter, and another is X-ray. So what we have to tell here that what is the technique we use for quantitative elemental analysis. Quantitative means you can calculate the what is the amount of that element is present. So do you know means what are these different kind of signal, like how a secondary electron generates, how backscatter electron is generates. So just basically this diagram is showing what are the different signal are generated. So one is let's say these are the beam electron when it is falling on the sample, it is interacting. So from this small layer OJ electron generates, then up to this layer secondary electron generates, then up to this layer BSC electron generates. So this total volume is basically known as interaction volume. So within this interaction volume different kind of signal generates. So and this transmitted electrons thing, it is for transmit TM. So means this transmitted beam. So this is the TM part and this is the ACM part. So you can just simply cancel out this one for this time being. So for ACM part now we have three answer. So three of you gave three different answer. Now let us find out which one is correct, right? So for this we have to understand what are these different signals are, how these signals are generating. So now let us go to the atomic level then. Now this is, let's say this is your atom, this is the nucleus which is positive charge, and these are the electrons. Now if the beam electron is coming, let's say this, okay. So now if the electron beam from the ACM, that your beam electron is coming, so what it can do, so it has two it kind of things happens. One is the elastic scattering and another one is the inelastic scattering. So elastic means, what is elastic scattering, you know? Anyone? Elastic scattering and inelastic. Shall anyone of you know that what is elastic scattering and inelastic? Okay, just so elastic scattering means when your electrons or that means no change in energy is there. Means that energy will be same before and after scattering, almost negligible change will be in the energy will be there. But in case of inelastic scattering, so most of the energy it will transfer to that sample. So there will be an energy difference after inelastic scattering. So BSC signal, it is because of the elastic scattering, and AC signal is because of the inelastic scattering. So now let us see what is BSC signal. So let's say this beam electron is coming and this is positive, nucleus is positive, right? So when it is coming near the nucleus, it will get affected by the electrostatic field of this nucleus, because this electron is negatively charged, beam electron, and this nucleus is positive. So it will just attracted by this nucleus first, and then it will bend and it will get out of the sample. So that's why it is called backscattering. Means it is coming back from the sample after scattering back from the sample. So that is the backscatter electron. So now I have described what is BSE electron. Now you can understand on which factor of that atom will influence this amount of the backscattering electron. What on which thing it will depend. Why backscattering happens? Because of the nucleus of the atom, right? So that means it is depends on the Z value. Z means atomic number. So it depends on the Z value. So like let's say miss for iron, what is Z? 56 is atomic number. 25, right? Or sorry, 28, right? Or for silicon, it is 14. So depends on this Z value, these things will means that number of the BSC electron will depends. So that means it will give you the idea about which element is present. That means you will get the elemental analysis you can do. But here this question asks quantitative elemental analysis. That means you also have to know what quantity it presents. So BSC electron can give you the idea which element is present, but at what quantity it cannot give you that idea. Okay. So who told that BSC electron? I think Manas, right? Okay. So BSC electron will give you just idea which element is present. So BSC will give idea which element, but how much it cannot give us that idea. So BSC electron will give you the Z contrast. Now what is secondary electron? Secondary electron is when this beam electron, let's say it is knocking out one of the sample electron. There was one sample electron, it knock out this electron, and then this electron come out from the sample. So this is basically sample electron. This electron coming from the sample. So this electron is secondary electron, and it is occurring because of the inelastic scattering, and also the energy of the secondary electron is very less. It is near about 50 volt boundary, that is electron volt boundary is there for secondary electron. So its energy is very less, means it can only come out very near to the surface. So let's say this is your surface of the sample, so only very thin layer of the surface it can come out. From the bulk it cannot come out. So as you can see in this previous, okay, diagram, right? Here also you can see this secondary electron only can come out up from this much area only, but BSC can come out from a larger area. So what contrast the secondary electron will give you? As it is coming very near to the surface, so it will give you the idea of the about the topographical contrast. So secondary will give you topographic contrast. It will not depend to which element is present. It will just depend on the surface. What is the nature of your surface? Let's say your surface is like this. Somewhere it is uh, depth is more, somewhere less. So let's say from this area more number of secondary electron can come out. But if it is false in this area, so it will scatter in many directions. Some of the secondary will get absorbed. So less number of electron will come out from this secondary electron. Less number of electron, and here higher. So this area will appear as bright, and this pores area, that is when that uh, will appear as dark. So it will give you a topography contrast. So it will not give you any idea about the uh, that which element is present or at what quantity. So these two answer is not right, BSc and secondary. So now there is another type of signal, that is X-ray. How X-ray, characteristic X-ray radiation occurs? So when this secondary electron emit out, so there creates a vacancy, right? Vacancy of electron. So this higher cell electron will jump to this vacancy, to this. Means- so this energy difference between these two cell will emit as a characteristic radiation. If let's say that ionization occurs in the K cell, and then from the L cell one electron jumps to the K cell, then this characteristic radiation is called K alpha. Similarly, electron if electron jumps from, let's say, L cell, so this one the L cell, so this is K, sorry, L, this is M. So if electron jumps from the L cell, then this is K alpha. If electron jumps from the M cell, this is K beta, like this. If K cell ionization occurs, then it is K characteristic radiation. If electron jumps from the L, it is K alpha. If electron jumps from the M cell, this is K beta. So this radiation is unique. that wavelength of this radiation is unique for different element. So there is a particular value for copper. So let's say copper K alpha, it is 1.54 angstrom. For others also that lambda K alpha. So this K alpha radiation has a unique value for different element. Let's as example for copper it is 1.54. You can also search for the other elements also. So you will find a unique value. So in this technique, using that characteristic radiation, you can identify which element is present. So this also you know. Now we need to know what element means how much element is present, how much, which we know how much. For this, for that we do that X-ray. It has a certain intensity. So let's say in your sample, sample is pure, and one sample you have that one alloy. So from you will take the intensity from the pure sample. Let's say intensity for pure means I naught or IP. I'm writing, or intensity of the from the alloy you get IA. So if you take the ratio, that is IA divided by the IP, intensity of the alloy and intensity of the pure sample. So this will give the idea how much of that element is present. So from the X-ray, you can get that how much of the uh, of that means quantitative elemental analysis you can get, like how much of a element is present. You can only get from the X-ray. Now you understood, right? Means how these signals are generated and why we are using X-ray for quantitative elemental analysis. Why secondary electron or BSc electron cannot give.
Yes, sir.
Okay. So just for a revise, what backscatter electron will give you the idea about? Okay, spectroscopy on which principle? Okay, I'm coming to this answer first. But just for a revise, let me know what is the what signal means what data you will get from the BSc electron. What kind of contrast?
Which element is present?
Uh-huh.
Which element will present
Yes, which
in the
element is present. So that means Z contrast you will get. That means which element. And from secondary electron, secondary topography, right? Just remember this thing from which signal, which information you will get. So it will be useful. And X-ray, which element and how much. And transmitted is for TM purpose. There is a many thing involves diffraction, dark field image, bright field image. So that is a other part of this microscopy. So now let's come to your question. So spectroscopy work on which principle, right? So spectroscopy means what? Spectroscopy means you have to like this is the spectroscopy only. I means you have to identify which element is present and how much quantity. So let's say this is your sample. So diffraction is different thing, spectroscopy is different thing. But both in both case you are using X-ray. So this is your sample. So let's say you are falling an electron beam on the sample, right? So now depending on the element present here, so different kind of wavelength will generate. Let's say there is iron is present. So one wavelength you will get from the iron. Let's say copper is also present. One wavelength you will get for copper. So here lambda is variable. So for spectroscopy, your lambda is variable. Now, so all this lambda are going together into your detector, right? So now let's say we have two type of detector for X-ray. One is EDS, another is WDS. You know, right? EDS means you separate this energy into a different energy level. Let's say you have this channel. So let's say this is from 0 to 2 volt electron volt. Let's say this channel is for 2 to 5 electron volt. So there is different channel is there. So depending on its that energy of the X-ray, it will store it here. And it will store some other lambda somewhere else. Let's say it stores copper here and iron here, let's say somewhere else. Okay. So this way it will just judge which element is present, how much quantity. It will just count per second it will give. Means this is count. Count means intensity and per second. Count per second. Let's say in first second this much of signal you got. In the next step you this much signal you got. In the next step this much. So this is one detector. Another one is WDS. So WDS, what it do here, lambda is variable, and so now you know Bragg's law, right? So what is Bragg's law? N lambda is 2d sine theta. So lambda is variable here. Now if you fix this d for a particular lambda, that theta will also be fixed, right? So in WDS, what it does is it does. So let's say this signal is coming for iron. Sorry, and this is for coming from for copper. The lambda is different for these two. Now you just place a single crystal here which has a certain d value. D value is fixed of this crystal. So what it will do, it will scatter this iron X-ray to a certain angle and this copper X-ray at different angle. So now depending on which element you are measuring, so your detector is placed here or here. So in case of spectroscopy, I am just summarizing this. Lambda variable, D is fixed because you are using a single crystal. So theta will also be depends on this lambda. So theta will be variable. So you are keeping the D fixed. Lambda is variable. This is for spectroscopy. But for diffraction, this is different. For diffraction, your lambda is fixed. Right? You are using a single wavelength in case of diffraction. Either Cu copper K alpha or cobalt K alpha. So this fixed lambda you use and you measure. D is also variable in this case and theta is also variable. So this is the difference between the spectroscopy and the diffraction. So this is the principle for spectroscopy and this is the principle for diffraction. So you got it, Manas? Okay. So okay, if everyone is okay with this question, then I can move to the next question. Anyone has any doubt? Everyone is okay with this?
Yes, sir.
Okay. Okay, then I am moving to the next question. So this is the question number 26 of GATE 2014 MT. So the question states that a metal powder with an apparent density of 2.5 gram per centimeter cube was compacted in a cylindrical die to a grain density of 5.5 gram per centimeter cube. If the height of the grain sample was 12 millimeter, then the fill height of the powder is in millimeter. We have to calculate. So before solving this question, anyone can tell me what is green density and what is apparent density? Anyone? What is apparent density? You guys all know about the sintering of a powder sample, metal powder, sintering of metal powder. What are the different stages involved in sintering? At least you can try to answer if anything is coming to your mind. From the name itself, it is you can answer, right? Apparent and
Sir,
green.
apparent density means actual density of the powder.
Not really actual, you can say.
Sir,
Yeah.
apparent density is the powder is a type of the arrangement will be more than, and green density is there is a move or and sintering powder that means the heated the powder certain melting point.
Okay. Okay. So just first, let us see what are the different stages in sintering. First, you have some loose powder, right? Let's say this is a loose powder, pile up of loose powder. Then, for how we will do sintering, we put this powder in a die first. So we have, let's say we put this powder in a die. So this is the piston. So we put this powder in a die. Then what we do? We first press it or compress it, right? So let's say we have compressed it up to this. So now your powder become much more compacted in the compacted form. Earlier it was loosely packed. Now it is compacted. This compacted sample is called green sample. Then we take out this compacted powder sample, that is the green sample, and put it in a furnace. So then this is sintering. So during sintering, what happens? That pores was there in between the powder. That part melted, and these pores are filled up. So this technique is basically sintering. At higher temperature, you are sintering this. You put up at the furnace at some temperature, depending on your sample or your operation. So now these are the different stages, right? So one stage you have loosely packed powder. So this now, sorry, what happened? I don't know what happened. Okay, now it is here. Huh. So this is loosely packed powder. So at this stage, what is your density? This is called apparent density. So density of the loosely packed powder is apparent density. Like here it is a die. You just pour your powder here. You don't compact it, just pour it in the die. So at that time, what will be the density of this powder? This will be the loose apparent density. We call this as rho a. Then you, let's say you compacted it. So when you compacted, then it goes into the next stage. There the density increases and it becomes much more compacted form, right? This is the piston. So there, this is row A, this is row G. Row G means green sample, density of this green sample after compaction. So this is known as green density. So in this question, row A is given, that is 2.5 gram per semi-cube. Row G is also given 5.5 gram per semi-cube. Now you understood what is the apparent density and what is green density.
Yes, sir.
Okay, so can you people just tell me what is the significance of the apparent density and what is the significance of green density? That's why these parameters are people use these parameters. Why it is important to know these parameters, green density and apparent density for a powder. What is the significance? let's say after BTech you become an engineer in some industry. So they send you to just investigate the quality of the powder. You are buying some powder from a vendor. So they sent you that which powder will be good for your operation. So you have to choose it, right? So that's at that time you need to know these parameters. What is the green density of that powder? What will be the apparent density of the powder? These parameters you need to know. But why you need to know these parameters? How you will just choose which powder will be good for you? At least you can try anything. If anything comes to your mind, you can answer.
सर ग्रीन डेंसिटी में होगा कि मतलब इसमें जो मॉइस्चर जगह वो नहीं रहेगा, और इसमें है कि ग्रीन डेंसिटी में मॉइस्चर रहेगा तो वेट कम, वेट जो उसका कम होगा तो इसका कॉस्ट से भी मतलब इसको रिलेट कर सकते हैं।
No, not moisture thing is there because in here you are not heating. So how moisture will go? You are just compressing the thing, right? So it is not related to the moisture. So what is the apparent density? Well, apparent density means when it is loosely packed. So how apparent density will change? Apparent density means the density of that powder because of its own weight, right? Or own flowability. If the flowability of the powder is good, then apparent density will be higher. Flowability means what? Let's say you are pouring this powder in a cylinder. If the flow ability of the powder is good, it will automatically flow means slide with each other, and it will just segregate in the compacted form already. Okay, so in this case your rho A will be higher. So if the flow ability is more, rho A will be more. So that means rho A will give you idea about the flow ability of the powder, right? So this is the significance of rho A. Much if your powder has much more flowability, then your rho A will be higher. So it is also good for your powder. You should have much good flowability. Otherwise, what will happen if you compress the powder? If the flowability is not good, so it will not compact in a will be compacted in a properly means that. Then what will happen? There will be a lot porosity will be there if the flowability of the powder is not good. So if the flowability is good, then you will have less porosity in your sample after compaction. Okay. So this is the significance of rho A. So you want higher flowability. Now, what is rho G? Rho G means it the density after compaction. So that means if rho G is higher means what it means? Ability of compact this powder is good. Means you will compact your powder at much more density. Rho G is higher means also your sample will have lower porosity, right? So rho G basically signifies the compressibility. So it basically tells you about the compressibility of the powder. Means up to how much extent you can compress this powder. So this is the rho G it tells you, and rho A tells you the flowability of the powder. Now you got it. What is the significance of these two? Understood this part, or you have any doubt?
Yes, yes, understood.
Okay. Now let us solve this question then. Okay. So what it tells initially, this powder was filled in a cylinder. So in that time, its apparent density was 2.5. Let's say height of the cylinder, initial height of the cylinder is h. Okay. So now it is compacted to a green sample. So now the powder is up to this level. In this case, rho G is 5.5. Now this height is given. So height of the green sample is given, that is 12. Okay, and this height is h. Now the area of this cylinder is A. If you consider this, the area of the cylinder is A. So then what will be the volume of the this powder sample? Volume will be A into H. This will be the volume, area into H. And what will be the mass? Volume into rho, right? Into rho A. So this will be the mass M1, let's say. So in this case, what will be the mass? Let's say M2. Mass is area into height is how much? 12. So this is your volume. So volume into density, that is your mass, right? So rho G. So now if we assume that when you are compacting this powder, there is no loss of the powder, that means that mass is same because you have no loss in the powder. So then M1 is M2. So your conservation of mass, that is mass is conserved, mass is same. So then what will be? It will be M1 is equal to M2. That means A into H into rho G means 2.5 is equal to A into 12 into rho G means how much? 5.5, right? So now A and A will get cancelled out. You have to calculate H, that initial, that fill height, that means initial height of the powder. So H, what will be H? 12 into 5.5 divided by 2.5. So what will be the answer? Just calculate and let me know. $26.4. Okay, another because minus how much you are getting? You are getting also same value.
Same value, sir.
Yes. So it is coming 26.4. So what will be the answer then? Fill height of the powder will be 26.4 millimeter. Yeah.
Sir,
So
1 minute, sir. Uh,
mhm.
Sir, here M1 or M2 are equal. But sir, in the case of area we are taking, the height are 12 mm, and the area should also be reduced in this case, Roji, in the case of
No
cylinder.
area why it will reduce because you can see in the question that you are compacted in a cylindrical die. That means it is your die. So this is a die, cylindrical die you have. Okay. So now we have filled your powder here. That's up to this lane initially you have filled. Now after some times you are just now you are pressing this powder with a piston. So you are pressing it and then now this level goes down to this. In a single die only, in a single cylinder only you are just compressing it. That means you are only changing the height. How the cylinder means area of this cylinder will change. It will be the same, na? You are compressing in a die. Means that means it is a rigid die. It is not the powder you cannot compress a powder without putting it inside a die or something, right? So that die
Oh,
is rigid. Like you just take a glass and then put some soil or put some soil inside and then just you press it with something. So that area of the your glass will change. Will it change? It will not change, right?
yes, yes, sir. Clear,
Yeah.
sir, clear.
So that when you are compacting it, that height of this soil level that will change, but that area of the glass will not change, right? So that means this area will be same only the height will be changed, and because of this height change you will have the volume change. And also as the volume is changing but mass is conserved, right? So here no loss of powder is happening because you just sealed it and you are just compressing it. So mass is also same, m1 m2 is same, but your high area is also same but height is changing, and because of this rho is also changing. So that is why this is apparent density, this is green density after compaction. Got it?
Yes, sir.
Okay. So anyone has any doubt with any of the question that are solved today? So we have solved these three questions today. One is this elastic modulus calculation, both in the transverse direction and in the longitudinal direction we have calculated. And what we found? We found that the elastic modulus in the transverse direction is less than the elastic modulus in the longitudinal direction. That means your composite is stronger in the longitudinal direction than in the transverse direction. So this was the first question. So the second question was what are the different signal that are generated in a SEM and which type of information we get from this signal. So we explained the secondary electron signal, we explained that backscatter electron signal and X-ray. So here one other type of signal is also there, that is Auger electron. So what is Auger electron? When this characteristic X-ray emits, this characteristic radiation, it also can knock out one electron from the sample. This characteristic radiation is also knocking out one electron. So this second electron that is knocked out by the characteristic radiation, this is Auger electron. So it will also have very less energy, even less energy than the your secondary electron. So this electron will also give you the means information very near to the surface because it also has the less energy. So only from near to the surface it will emit. See this, if you use this signal you will get very high good resolution because from a small area it is or a small volume it is emitting. And also as it is emitting because of the characteristic radiation, so you can use this signal for chemical analysis also. Okay, so this was the second question. And third question was this one, this apparent density and the green density of the powder was given, and what was the fill height we had to calculate it. Okay, so anyone has any doubt with these three of this question, or all are okay with it? Okay, so if no one has any question, then we'll close for today. So just attend in the next session in the on next Friday, and I will request that if you can tell your friends also to attend this session. If they find it helpful, then this will be good for the preparation of the gate also. And while preparing, if you people have any kind of doubt you are facing in any of the subject, you can ask me the question. If I will try my best to answer those questions also. Yes, recording of this live session I am putting on the YouTube. So you can just go to my channel and there you can just see the recorded video also. So the channel link, okay, let me share it again. So after live session, I am putting the video here. So that you can later follow this solution also. And if you have any doubt, then you can ask me in the next session also. Regarding any other doubt, if you have while you are studying, if you are facing any difficulties in any of the subject, you can just ask me. I will try to answer those things also. This is a kind of live mentoring session. Like so, only solving the gate previous year question is not the purpose. The purpose is basically to interact with you people more, so that you people also can find it very helpful. Okay.
Okay, sir. Thank you very much.
Okay, then we'll meet in the next Friday.